Hello, good morning. Am I audible?
Yes, sir.
Okay, good morning and welcome to a lecture on advanced power electronics. We have completed the theory of multi-level inverters, and yesterday we started with discussions of applications of multi-level inverter. Yesterday we discussed one application of multi-level inverter, that will be a DC to DC converter, and this DC to DC converter particularly we are using for high voltage DC applications. So here, so whatever we're getting the DC voltage, it may be in kV. We have seen that it is 100 kV or 50 kV, 80 kV, and current may be a less. Current may be hardly 1 ampere, 2 ampere, and one of the such application is a ESP, electrostatic precipitator, used in thermal power plants for air pollution control. Now, next application we are going for is non-regenerative AC drives, where our regenerative braking is not required. Some applications where we don't require the regenerative braking, and these applications, if you take an example of pump, you can take an example of pump used in chemical industries, or maybe used in water distribution system. In that case, we have seen that once pump is on, it may be on for 24 hours. So it is not a frequent on and off operation. These applications, if you see it here, once the fan is switched on or pump is switched on, it may be on for a week time. Okay. Similarly, the cases in case of a process industries. So we don't require a regenerative braking when we don't want to stop the machine frequently. Whereas pumps, fans, when you stop it because of the fluid or air, it will be automatically get the braking effect. So some applications, what we are listed here, pumps, here induced draft and post draft fans used in air circulation in the boilers, particularly this induced draft and forced up fans are used in the boilers, circulation of air in the boilers. Once they are on, it will be remaining on. We want to control the speed of this to control the flow of air in the boiler, where we have seen that combustion of the coal is taking place. Similarly, another application is the compressors. So these applications where we don't require a frequent start and stop. That is one thing, and we don't require the regenerative braking. So our drive will be a non-regenerative braking, but braking arrangement should be there. And for electrical braking, we are using the another method that we can call as a dynamic braking. Suppose you want to break this drive, here at the DC link we are having a, when you want to break the drive, we have seen that okay, our sleep is become the negative, and when sleep become negative, our induction machine will work as generator, and it will, through these diodes, a DC power will appear here, and this DC power is not going back to the supply, and here whatever power generated by this induction machine will be dissipated by closing this switch. When you want a regenerative braking, sorry, when you want a dynamic braking, during this we close this switch, and so that whatever power generated by the induction machine during the braking period, that will be dissipated in this resistance. So along the DC link we have to put a resistance and a controlled switch, maybe IGBT we have to use here, and by closing this, whenever braking takes place, we close this switch, so energy generated during the braking will be coming at the DC link, and then this energy is dissipated in the resistor. And particularly these drives, induction motor drives, we are using the speed control with variable voltage, variable frequency, that you are already studied one full subject on the industrial drives and control. So we use a variable voltage, variable frequency, a particular principle for controlling the speed of the induction motor. And we have seen it here. This particularly we are going for a multi-level inverter, because these drives particularly they may be rated voltage maybe a 3.3 kV or maybe a 6.6 kV drives. So these drives are medium voltage drives, what we can call as 3.3 kV or 6.6 kV, and capacity may be in megawatt range. So medium voltage and megawatt range induction motor drives, we are going for a multi-level inverter. And here for multi-level inverter, we have seen it here. This is a particularly we use the 3-level MLI. This is a 3-level diode clamped multi-level inverter we are used for the this particular drive. And our rectifier is, we are regenerative, non-regenerative drive. So here we are going for a conventional rectifier, conventional diode bridge rectifier, and these two diode bridge rectifiers, they are connected in series. A first diode bridge is of 6 pulse, other is 6 pulse, so it will become a 12 pulse configuration. And yesterday we discussed, for obtaining a 12 pulse, whatever supply we are giving to the first bridge and supply giving to the second bridge, they should have a phase shift of 30 degrees. They should have phase shift of 30 degrees, and because of that we are getting a 12 pulses in the period of 2 pi. Because of the star delta, star winding and delta winding, we have seen that fifth and seventh harmonics are eliminated from the supply. So here harmonics will be reduced. That is the benefit of 12 pulse rectifier. So here we have seen that with the help of this particular transformer configuration of fifth, seventh, these harmonics, predominant harmonics are completely eliminated, and dominant harmonic is 11th and 13th harmonic. So that is a benefit we can get with this configuration. So this is a non-regenerative drive where we use a diode clamped multi-level inverter, and it is a 3-level multi-level inverter. Now here rectifier pulse number is 12. We can go, maybe configuration is possible 18 pulse rectifier, or also it will be a 24 pulse is also possible. So whatever this we have discussed this, and this drive is again a 4-quadrant drive. We can run in the both directions, forward as well as reverse, by changing the phase sequence. So we change the direction of rotation of induction motor by changing the phase sequence. And here we are having a dynamic braking, so we can break the drive. Dynamic braking is there. So this drive, quadrant operation of this drive is the 4-quadrant induction motor drive. Now one question is there, can this drive will be used for rolling mills? What will be your answer? So whatever this drive we have studied, can it be used for a rolling mill? In case of rolling mill, frequently we have to reverse the direction of motor, direction of rotation of motor. 1 minute or 2 minutes is running in forward direction, again stops and runs in the reverse direction. Similar to rolling chapati, while rolling operation is similar to we have to make the chapatis, okay, in our house. So that particularly we have to change the speed frequently, rotation of direction we have to change frequently, and that's why this particular drive is not suitable for rolling mill application. Now let us, this is the panel we have shown it here. Just it's from the photograph of Siemens, okay, a manual or data book we have taken from this Siemens drive panel. So voltage is a 3.3 kV to 7.2 kV, and a 4.8 MVA capacity. And here what configuration they are used is whatever we discussed. They are using the rectifier, 12 pulse rectifier. So what are the same configuration what we are discussing? So whatever the which configuration, same configuration is used in the particularly panel. So here it is a 12 pulse rectifier, then 3-level neutral point clamped inverter section with IGBTs, This is a control cabinet. Okay, and dimensions of just it is a 2.4 meter wide and 2.2 meter is the height of the panel and 1.2 meter is the depth of the panel. So it is three cabinet and you can see. This is the particular, if you see at the top, we have seen that we have used the fans, particularly for force circulation of the uh, inverter devices, stacks, cooling of this we can done with the help of a force air cooling. Now let us go for again same the non-regenerative AC drive. Non-regenerative AC drive, and in that case, okay, again the applications and same water we have discussed. Only thing is their configuration is different. Now here we can use a thyristorized converter. We can use our diode. We can use it here. Okay, so here they are giving us a this is a particularly here you clear this. Okay, you can assume a 6 pulse uh, inverter. So here it is a lower side diodes. Okay, symbol is missing, we have to correct it. So all are thyristor. This is 6 pulse converter, this is 6 pulse converter, and this is 6 pulse, and they are added series so that it will be a 18 pulse converter. We are having a 18 pulse, and for getting 18 pulse, whatever line voltage of first converter, second converter, and third converter, a phase shift in the line voltage, a phase shift in the line voltage of first converter, phase shift in the line voltage of second converter and third converter, phase shift between first converter, second converter, and third converter, they should have phase shift of 20 degrees. They should have phase shift of 20 degrees. So here we are using for getting a 20 degrees phase shift. With respect to delta, here we assume as the this is 0. Then we are having one another configuration we can call as extended delta. Whatever the symbol, if you see here, this symbol is for extended delta. Delta is there, but again it is extended, and based on that, by adjusting this extended length, we can adjust the angle, this, and you see it here, just this here, looking at this. Okay, phase can, that is okay, transformer connection group, this we can call as a extended delta. So two extended delta, one extended delta will provide a phase shift of plus 20 degrees with respect to the central. So it is 30 degrees leading, 20 degrees leading with respect to these delta line voltages. Whereas with respect to these delta line voltages, this extended delta, you just see it here, there is change in the connections, and here we'll get a minus 20 degrees phase shift. So three line voltages, they are having a phase shift of 20 degrees. Three line voltage means three voltages supplied to the three phase voltage supplied to a rectifier 1, rectifier 2, and rectifier 3, and they have a phase shift of 20 degrees with respect to each other in the line voltages. And so we get the again the 18 pulse. Here why we are going for series configuration, we require a higher DC link voltage, maybe here more than 3.3 kV drive, definitely we require maybe 5 to 6 kV DC. So with this high voltage DC, we can obtain with the help of this. At the same time, here we have seen that our primary of the transformer is star connected. This is the primary of transformer, and we are having the three secondaries. So three phase transformer, in that case primary is star connected, and we are having three secondary windings on the transformer. One is connected in delta, other is connected in extended delta, and third is also the extended delta. And purpose of this is, okay, you can get a better quality, or it should not inject the harmonics into the supply. Now looking at this, again we are using what type of braking we are using here. Looking at this, what type of braking we are using to this drive. What is the name of braking it is used for this drive? Am I audible?
Yes, sir.
What type of braking? Name of the type of braking? So we connect a resistance across the DC link, and when machine is braking takes place, this power will generate the stored energy in the rotating parts will be converted into electrical, converted into DC and coming at the DC link. And this power is not going to the grid because this power flow is unidirectional, only from AC to DC side. So here voltage will build up, and based on that, we turn on the switch, and so that whatever power generated by the induction motor during the braking will be dissipated in the resistive load, and this braking we can call as a dynamic braking. Is it clear? So in case of non-regenerative AC drives, we use the dynamic braking. Very less required, but it is the must. So any question on this? Hello?
No, sir.
Yeah. Now, can you identify what is the level of this multi-level inverter? If you're looking at this diagram, can you just tell me what will be the level of this multi-level inverter? Is it a 3 level, 4 level, or 5 level? In case of 3 level, how many devices are there? Upper half and lower half in the one leg. In case of 3 level, we are in 2 devices. Is it right? In case of 5 level, we are having 4 upper devices and 4 lower devices in the same leg. So here in the upper, okay, one leg upper we are having 3 devices, lower we are having 3 devices. So what is the level number here? Can you just try to answer? What will be the level?
Fourth level.
It is a 4 level, correct. Whenever 5 level is there, we are having 4 devices in the upper half and 4 devices in the lower half. 3 level is there, we are having 2 devices in the lower upper and 2 devices in the lower. Now it is 3 means this particular level of the multi-level inverter is the 4 level. And what is the topology? What will be a topology of this multi-level inverter? Name of the topology?
Flying capacitor.
Topologies, is it right? So what is the name of this topology? Anybody? See how many
Flying
people are
capacitor.
joined today? So what is the name of topology? Hello, what is the name of this topology?
Flying capacitor.
Okay, so we are having a flying capacitor topology, and we have seen that almost 34 students are joined. Is it right? Just the 34 students. Okay, we have to give the attendance to the authorities, higher authorities. That should be also we have to keep in mind. Okay, so we are having a 4 level flying capacitor multi-level inverter and 18 pulse converter and a dynamic braking, and again applications will be the same. What are applications of this drive? High power drives for pump, high power drives for ID and FD, induced draft and post draft fans used in boiler, and the very big capacity compressor drives. These are the applications. So whatever we are used, so no regenerative braking, we are using a dynamic braking. And what inverter we are using? 4 level flying capacitor MLI, then 18 pulse converter. And how to obtain 18 pulse converter? We require the phase shift of 20 degrees voltage applied to first bridge, second bridge, and third bridge. That voltage should have a phase shift of 20 degrees plus minus 20 degrees. How to obtain that? We are having a particularly connection known as extended delta. Okay, so with this now we can go for another again a non-regenerative drive, means we are using a dynamic braking. We are using the dynamic braking, and here if you see it here, what we are having is again here our rectifier. If you see it here, now we are using the extended star. If you see here, we are using the star, and again it is extended star. It is a 6 pulse bridge. So total configuration is the, from the supply it will be a 18 pulse. This give a 6 pulse, this give a 6 pulse, this will give a 6 pulse. So again here we are having a 3-phase transformer, primary star connected, and we are having the 3 secondaries. One secondary is star connected, another secondary is again it is called as our zigzag type connection. Extended star you can call it zigzag. This connection you have studied, this is zigzag connection. Okay, and this is a zigzag connection. With the help of that we can obtain a phase shift of again the 20 degrees, plus 20 degrees and minus 20 degrees. And here we have seen that we are using these rectifier bridges, diode bridges. They are not connected in series, they are having a separate. So we are having, this is we have shown for one leg of the inverter. And if you see that this is, we are having one H bridge. This is a one H bridge. This is second H bridge. Sorry, I have to use the laser. So this is a one H bridge. This is a second H bridge, and this is a third H bridge. And these 3 H bridges are connected in series. So our multi-level, this is for one leg. Whatever we have shown, this will be one leg of the particular inverter. Same circuit we repeat for phase B and phase C. Phase B and phase C. So this one bridge rectifier unit, rectifier bridge, it is for one leg we require 3 bridge rectifiers. Another leg also we require 3 bridge rectifiers. So another leg also we require 3. So total we require 9 bridge rectifier bridges. Totally we require the 9 rectifier bridges. Is it clear? How many 6 pulse bridges are required for this configuration? We require a 9, because one phase require 3 bridges, because we are having 3 H bridges are connected in cascade. So what is the level number when we connect 3 H bridges in series or cascade? So what should be the level of the multi-level inverter? When 3 H bridges are connected in cascade, what should be the level of cascaded H bridge multi-level inverter? Hello, am I audible? Response is required.
5, sir.
Again, I am telling. So first H bridge is giving how many levels? First H bridge is giving how many levels? First H bridge is giving 3 levels. Is it right? And successive, it will give the 2 levels. So here, the first lower, you assume that it will be a 3 level. Then we add 2, it will be a 5. Then we add another 2, so 7. So what is the level of this particular cascaded H bridge multi-level inverter?
7.
7 level. So this particularly H bridge inverter is having a 7 levels. Okay, 7 level cascaded H bridge multi-level inverter. This is a one leg, or you can call as one phase of the inverter. And one phase, each H bridge required separate supply, and for that is obtained with the help of a one rectifier bridge. And one leg we require 3 rectifiers. Another leg also requires 3 rectifiers. Third leg also requires 3 rectifiers. So total number of 6 pulse rectifiers will be how much? 9. We require 9 rectifier bridges, 9 H bridges. One H bridge we have shown it here. So we require 9 H bridges, and we require here we are required. This is a separate. So this is a how many secondary windings we require? 3-phase winding. One leg require 3 windings. Another leg require 3 windings, and third leg require 3 windings. So what is we are having a transformer? Primary is having one primary winding, and how many secondary windings? Can you imagine what is the transformer? We are having one primary winding which is a star connected, and how many number of secondary windings we require? How many secondary windings we require? One leg requires 3 windings, separate winding. This is one 3-phase winding, this is another 3-phase winding, this third 3-phase winding. So one leg requires 3 windings. Another leg requires 3 windings. Third leg requires 3 windings. So we are having a 3-phase transformer. You see that we are having one primary winding and how many secondary windings?
9.
But 9 secondary windings. I imagine what is the complexity involved in that. We are having a 3-phase transformer. With that, we are having only one primary winding, star connected, and we are having a 9 secondary windings. Normally, our power transfer is one primary winding and one secondary winding. But here, particularly for this drive, we require one primary winding and 9 secondary windings. 9 secondary windings. That is the complexity of this particular drive. So this is a cascaded H bridge multi-level inverter. Number of levels are 7. We require 9 rectifier bridges, isolated supply for each H bridge, and then we are having a 3-phase transformer. Here we are in zigzag connection, you can call it, or extended star, you can call it. We require a phase shifter. Is a 20 degrees, plus 20, 0, and the minus 20. So we require one 3-phase transformer where we are having one primary winding and we are having a 9 secondary windings. Okay, so that will be what we have discussed here. This is just we have listed it here. Now let us go for this regenerative drive. Okay, this will be a regenerative drive. So what is this? It is our 3-phase supply. Okay, so this is a 3-phase supply. We are having inductances, and this is what type of multi-level inverter? What is the name of the multi-level inverter or multi-level rectifier? You can call as PWM rectifier and PWM inverter. What is level of this? What is the level of the multi-level inverter? It is a 5 level, 7 level.
5.
Hello, it is a
5.
how many devices in the upper half and lower half? How many devices in the upper half? Okay, one leg. We are taking output. Okay, upper you can call this and lower you can call this. So how many devices in the upper half and how many devices in the lower half? 2 devices, is it right? 2 IGBTs in the upper half and the lower half from the output where we are taken. So what should be the level? What should be the level of this?
3 level.
3 level. So correct. So this particularly we are having a 3-level diode clamped multi-level inverter. Motor side we can call as this is the 3-level diode clamped multi-level inverter. Connect to the motor side. So it is working as the inverter, let us assume. And this is supply side. Earlier we are using the diode bridge. Up till now we are using the diode bridge here. Is it right? This we are using the diode bridge here. But now we replace the diode bridge with the PWM rectifier. And now what is again? It is a 3-level diode clamped PWM rectifier. This is a 3-level diode clamped multi-level rectifier. Okay. So what is the benefit of this 3-level diode clamped multi-level rectifier? What is the advantage of this scheme? What is the advantage of this scheme? From supply point of view, what is the advantage of PWM rectifier? This is a PWM rectifier. Is it right? We have spent 10 lectures on PWM rectifier. We spent 10 lectures on a PWM rectifier. So what is the advantage of PWM rectifier?
Source current is sinusoidal.
Okay, one advantage, correct. What is the other advantage?
We can work in any power factor.
Okay, or we are more interested at unity power factor. So from supply side, so whatever it takes a sinusoidal current at unity power factor. That is the advantage of the PWM rectifier. So now this drive will work in all the 4 quadrants. It can run in forward, backward direction or forward or reverse direction. And the braking is a regenerative braking. Okay, whenever a slip becomes positive, this inverter will now become as a PWM rectifier. and this PWM rectifier will become as a PWM inverter. Power flow can be reversed, and whatever power generated during the braking is feedback to the supply. So this drive we can call as a regenerative braking is taking place. It can run in 4-quadrant regenerative AC drives. Okay, so what is the benefit? It is a medium power induction motor, medium voltage induction motor, 3.3 kV or 6.6 kV. We can use a multi-level inverter. The topology is diode clamped 3-level MLI. This is a PWM rectifier. We spend almost 9 lectures on PWM rectifiers. So it's a multi-level PWM rectifier. So it takes a sinusoidal current from the supply, works at unity power factor, power flow is bidirectional, and this is a 4-quadrant regenerative DC drives. We use the applications. We are already discussed the 4-quadrant operation. Okay, same slide I have kept it here. Okay, we are not going to discuss this, and the applications of this will be the traction drives, electric drives, locomotives. Okay, a rolling mill drive just we discussed, lift and the elevators. These are the applications of this a particular drive. So that will be our recent drives available. If you this is our recent drives available from maybe a Siemens or okay, and maybe any ABB or Schneider, whatever it, they are having this front end is of PWM rectifier. So this will be a we don't have any power quality issues with this particular AC drives. Now here we are going for again, here we are regenerative AC drive, we are going for it. And how we get a simplification, if you see it here. Again, if you see here, this is a multi-level inverter. What is the cascaded H-bridge multi-level inverter? One leg we have shown it here again. How many levels here? 3 plus 2 plus 2. So it will be 7-level cascaded H-bridge multi-level inverter. And this H-bridge multi-level inverter requires isolated supply, DC supply. But here, how the isolated DC supply is obtained? If you see here, how the isolated DC supply is obtained? Here, how we obtain the isolated DC supply? Is it we are use the diode bridge rectifier? Is it visible to you? Is it we use the diode bridge rectifier? Is it here we use a diode bridge rectifier? What is your answer? We don't use diode bridge rectifier. What we are used here? We use a PWM rectifier. We use the PWM rectifier. And what is the advantage of PWM rectifier? Sinusoidal current, unity power factor. So each H bridge is supplied with a PWM rectifiers. And how many PWM rectifiers will require for this total drive? How many PWM rectifiers will be required for this total drive? One leg requires how many PWM rectifiers?
3. So total
3.
9.
So we require total 9 PWM rectifiers. Okay, so we require total 9 PWM rectifiers. Each PWM rectifier is having a 6 devices. So 9 into 6. How many IGBTs we are having? 54 IGBTs. How many H bridges we require? One leg we require 3 H bridges. So 3 leg we require 9 H bridges. Okay. And here we have seen that our transformer is now not necessary to be the 18 pulse configuration, because here there is no problem of harmonics. No problem of harmonics. Currents are sinusoidal. So use the star delta conventional transformer. Nothing matters. We don't go for a complexity in the transformer connections. Our transformer connection is simplified because whatever secondary currents, these are the sinusoidal currents and unity power factor. So no problem with that. So we use a very simple transformer here. Primary star connected. And how many secondaries here? One leg 3, another leg 3, and third leg. So we are having a 9 secondaries. Same configuration, but we just replace this instead of diode bridge, we use a PWM rectifier. And if you use a PWM rectifier, definitely our transformer construction is simplified. Now we don't require a delta, extended delta configuration or star and zigzag configuration. We use simple transformer connection that can serve. Again, it will be a regenerative. Why it is a regenerative? Because PWM rectifier is bidirectional. So now our drive will be a 4-quadrant and the regenerative braking because power flow is both directions. Again, so it is a bidirectional. It means traction drives, rolling mill drives, lifts, and the elevator drives. So this is all about our applications of regenerative and non-regenerative AC drives. Okay, so we are just listed once again the applications of this regenerative 4-quadrant AC drives, high power down hill conveyors. Okay, water conveyors we are using in case of mines also. We can use these drives. High power regenerative applications such as traction drives, steel mill rolling drives. Okay, and the mill drives used in the cement plant also. So is it okay? So one application of multi-level inverter we discuss almost 40 minutes is the induction motor drives or the AC drives with the help of multi-level inverter. Any question on this? Hello? Any doubt regarding the drives? AC drives, we use the AC drives and these drives are fed from multi-level inverters and we consider all topologies. Diode clamped, flying capacitor and the cascaded H bridge. We consider also the regenerative braking and the non-regenerative or the dynamic braking of the AC drives. So any question?
No,
Hello,
sir.
any doubt?
No, sir.
Okay, so let us go for another application. This will be a topic related to the power system. We are already discussed this in case of in case of our PWM rectifiers. So here if you see at the diagram, if you see this at the diagram, we are having a reactive load and this is we are going for reactive power compensation. Another name you can call as a power factor improvement. Okay, one is you can call as the power factor improvement, a reactive power compensation. Why we require reactive power compensation? In case of transmission network, we require the reactive power for maintaining the voltage profile. And now instead of using the capacitor, one option is the for reactive power compensation, we have to use the capacitor or inductors. Instead of physical capacitors and inductors, we can use the multi-level converter. A general term, multi-level converter means PWM converter, PWM inverter you can call, or PWM rectifier you can call it. We can use this. So here we can use a PWM rectifier, a multi-level PWM rectifier we can use for, and we have discussed already, PWM rectifier can work at unity power factor, leading power factor and the lagging power factor. And how to identify or how to make it here. So it is if you want to have a zero lagging or zero leading. Here we have seen that here power flow is only reactive. Are you getting that? This bridge, if you supply here, power flow between the supply lines and this multi-level converter is only reactive. Only a reactive. So you are knowing the load angle. Looking at this difference, looking at this diagram, how we define the load angle for this case. Looking at this diagram, what will be the load angle, how we define a load angle for this circuit configuration. Angle between two voltages we can call as a load angle. Here looking at this diagram, angle between which two voltages we can call as the load angle.
VC and VS.
Angle between the VS and VC. Okay, we are just showing a generalized diagram. So angle between the supply voltage here called as a VS and the VC you can call as a rectifier back EMF here, whatever we have shown it here, and angle between them we can call as the load angle. And load angle is required only when we require a active power flow. Our application is we are having only the reactive power compensation, only with the reactive. So what should be load angle? Load angle will be 0. Is it right? For reactive power compensation, we don't require the load angle. Very small angle is there. Okay, we neglect it to meet the losses in that. But now we assume that load angle is 0 for simplicity. It means that Vs and Vc, they will be either in phase or out of phase. Load angle is 0. It means that whether they are in phase or out of phase. Sorry, they are in phase. But now the magnitude of Vc can be controlled. Is it right? The magnitude of Vc can be less than Vs or can be greater than Vs. How we control the magnitude of Vc? How we control the magnitude of Vc? That is nothing but back EMF inverter, we can call it. So this particularly, this let us assume that our 5-level diode clamped multi-level inverter, and if you want to control this Vc, means we have to control the modulation index. So magnitude of Vc can be controlled by controlling the modulation index. So we can control the Vc. Also our phase angle is also we can control by the multiple carriers sinusoidal PWM. With the help of that, both we can control the amplitude of the Vc and phase angle of the Vc. But here our phase angle is 0. We maintain Vs and Vc, they are in phase. And but now here magnitude of Vc can be controlled by controlling the modulation index of this PWM technique, a multiple carrier sinusoidal PWM technique. We can control the modulation index to control the Vc. And our Vc can be a greater than Vs or Vc can be a less than Vs. And when our Vc is greater than Vs or magnitude of Vc is greater than the supply voltage, then it will take a leading reactive power. And when Vs is less than or Vc is less than Vs, when Vc is less than Vs, it will be a lagging 0 power factor. So here these two diagrams we have shown reactive power compensation. So here if you see here a phase angle is 0, Vs and Vc, they are in phase. And what is our expression? Vc plus the reactive drop, Vc plus Ixs, Vc plus Ic into Xs will be equal to Vs. What is our equation we have to use here? Vc plus Ixs drop, Ic Ixs drop will be equal to Vs. So with this equation, we have seen that when Vc is greater, you see the arrow of IXL drop, ICXS drop, it is towards the left. And our reactive current will be lagging the inductor voltage by an angle of 90 degrees. So to this 90 degrees, so this will be our IC. And IC is now with respect to Vs is leading by an angle of 90 degrees. So this is our, we can call it a 0 leading power factor. Or this particular multi-level converter takes the leading reactive power. It works at the leading power factor. This we have shown it. Now when it works lagging, we just reduce the magnitude of Vc less than Vs. So now Vs we are having higher and then Vc is less. And our Vc plus ICXS. So this is now the phase of ICXS. Position of ICXS is reversed by 180 degrees. Now earlier it was towards left, now it becomes the direction towards right. And lagging to that 90 degrees, we are having IC, and now our IC will be a 90 degrees this. Okay, so this will be a, okay, we can call as a reactive power compensation. And what is the name we can give it in case of power system? When we use a multi-level converter, voltage source converter for reactive power compensation, in case of power system, we can call as a STATCOM. This particular we can call as the STATCOM. Is it okay? Any questions on this? Reactive power compensation, where we can use in the transmission network, we have to support the reactive power to maintain the voltage profile. Sometimes we have to require a leading in the when load is very high, we have to supply the reactive power. And during midnight, okay, we have to supply the lagging reactive power. That can be possible with the help of a STATCOM. And this STATCOM is nothing but our multi-level PWM rectifier, and this can work as pure inductance and the pure capacitance. This configuration is a pure inductance, it will work, pure capacitance, it will work. It is not required a large value of physical inductors and the capacitors. Our voltage source converter will make the job of inductor and the capacitor. So any question on this? Any doubt? Hello? So this is called as STATCOM. Okay. Distribution side, it is called as DSTATCOM. So any questions? Am I audible?
No doubt, sir.
Okay, then let us go for last bit of this. That is back-to-back intertie. You are in full one subject on HVDC. Is it right?
Yes, sir.
Yes, sir.
Yes. So what is the pulse number we are using for the HVDC? Which devices we are using? Which devices we are using in the converter and inverter of HVDC? Which devices we are using? Devices
GTOs
means
or thyristor?
okay, we are using the thyristor, and normal configuration is a 12 pulse rectifier and 12 pulse inverter. And what is the drawback of this 12 pulse rectifier and inverter? It injects harmonics. It takes a Cauchy square wave current from the supply. It takes a Cauchy square wave current from the supply. 12 pulse, what will be the dominant harmonic? In case of this HVDC, which will be a dominant harmonic injected into the supply? In case of our
12K plus
HVDC,
minus 1.
how much?
12K plus minus 1.
Okay,
11
12
and 13.
n plus minus 1. So if you n take 1, so dominant harmonics are 11th and 13. And we require the filters for that. Okay, all this. That will be a part of our HVDC. But now this 12 pulse thyristorized converters we are using at working as a rectifier and inverter. Instead of that, we can use the PWM rectifier. Here we can use the IGBT or GTO. High power applications, we have shown here a GTO. You can show it here as a IGBT. A multi-level PWM rectifier and multi-level PWM inverter. Is it right? So thyristorized converter can be replaced with multi-level PWM converter and inverter configuration. PWM rectifier or PWM converter, instead of 12 pulse converter, we use a multi-level PWM converter. Multi-level PWM converter. And multi-level PWM converter, in general, it can work as a rectifier as well as the inverter operation. And benefit is that our currents are sinusoidal. We can operate at any power factor. So there is no problem of harmonics. We don't require the filter. And here we have seen that we can call as a back-to-back intertie. Means here it is a DC link is there, but it is in the same station. So rectifier and inverter panels both are in the same station. They are not at the different places. They are at the same stations. Whereas in case of HVDC, we are in one station at Padge and one station at Chandrapur. Okay, but here both are at the same place. Okay, there is no DC transmission. Here there is no DC transmission. Just we are having a connection because it is in the same substations. We are having a rectifier unit and the inverter. And how we control power flow here? Let us assume that power is, this is supply side. We have to go to the another system. So here we are having a VS and a voltage at the input of this. That is we can call as a VC. So by controlling the phase angle of VS and VC, are you seeing that this is the voltage called as VS? The supply voltage we can call as a VS, whereas back EMF of this particular PWM converter we can call as a VC. So this LS inductor at the source side we can call it. One side we are having a voltage VS, other side we are having a voltage VC. and this VC we can control with the help of controlling this PWM converter. VC we can control. Which parameters of VC we can control? Which this voltage we can call as VC. Is it? You are seeing this voltage we can call as VC. And which parameters of VC we can control? Which parameters of VC we can control? Can we control phase angle? Can you control amplitude, or both? VC, we can control the phase angle as well as magnitude.
Amplitude.
Both we can control with respect to Vs. And it is also possible. Then now, if you see here, now this is the first case. Vs is leading to the Vc. So power is flowing from Vc to Vs or Vs to Vc. Vs is leading Vc by an angle of del. So power is flowing from Vs to Vc or Vc to Vs?
Vs to Vc.
Power is flowing from Vs to Vc. So power is flowing from Vs to Vc. Okay. So here we are flowing. And we are no Vc plus I excess drop will be equal to Vs. And lagging to that 90 degrees. This is our Is. So this will be Is. So now here supply current is what? Leading. So this particularly converter takes a leading current from the supply. Okay. Then now if I change the amplitude of Vc, I now increase the amplitude of Vc. Okay, I increase the amplitude of Vc, and then we have seen that it is a excess drop. Okay, now particularly become it will be 90 degrees to this Vs, and we have seen that to Is excess, our Is will be lagging by 90 degrees, and in this case operation we can call as a unity power factor. Now if you reduce the magnitude of Vc with respect to Vs, now we see that this is the position of Ix's drop. So Ix's positions you can see it. Now the current will be lagging. So here we can control the active power as well as the reactive power. Okay, and here power is flowing from the, similarly here we can control VL, and here you can call as okay, load side. This angle also we can control completely, so that power from will flow from one AC system to the other AC system. So here system frequency may be 50 Hz, here system frequency may be 60 Hz. Two different frequency system we can connect together. If you want to give the power to the neighboring country and their frequency is different, then this may be the configuration. They are operating at 60 Hz, we are operating at 50 Hz, and if you want to give the power flow to the other country which is having a different operating at different frequency, then definitely this configuration we can use. This is also called as HVDC light. When we use a PWM, instead of thyristors we are using the PWM converters, then term we are using is the HVDC light. So here this is a back-to-back intertie. We don't have a DC transmission here, and power flow can be controlled from this side to this side or this side to this side. We can control the source power factor at both sides, as well as okay, our currents are the sinusoidal. So this is the almost all applications of back-to-back intertie. One application is there that okay, UPFC. I think you are going to study. I am not taking this. We are running out of time. Okay, so we have to now we have completed the 2 modules of this, and next time, particularly on Tuesday, we start with the next module. I'll send the PPTs of UPFC. You can prepare yourself. Okay, is it right?
Yes,
Any
sir.
questions? Hello. So we meet Monday at 1:15. I will send the file of our next experiment so that we can demonstrate the next experiment on the 27th of September. Is it okay?
Yes, sir.
Yes, sir.
Yes, okay. So thank you, and we meet on Monday at 1:15 p.m.